In this video, we're going to be discussing exponential growth and decay problems. Let's look at this exam question. It says, the value of a car V can be modelled by this equation. This says that t is a real number, t is greater or equal to 0. It says where the age of the car is t years. So V stands for the value and t stands for the age of the car in years. Using the model, we're asked to find the initial value of the car. So we're asked to find V when t equals 0. So all we need to do is substitute in t equals 0 into this equation. That gives us this, which simplifies to this. And we know that e to the power of 0 is 1. So evaluating, we get 18,000. Therefore, the initial value of the car is £18,000. Let's look at the second part of this question. It says, given the model predicts that the value of the car is decreasing at a rate of £500 per year at the instant when t equals capital T, we're asked to show where this equation comes from. This is talking about a rate of change. It's talking about the rate of change of value over time. That is dv by dt. And it says that this rate of change is decreasing. That means that dv by dt is negative. In this case, negative 500. If it had said that the value was increasing over time, then that would be a positive sign instead of a negative sign. We had this equation. We can now differentiate this equation with respect to t to make use of this equation number 1. How do we differentiate an exponential like this? Well, we differentiate the power. That, in this case, gives us minus 0.25, and that comes to the front. How do we differentiate this plus 2,300? Well, that just gives us 0. It's a constant. Simplifying, using the calculator, we get this. Now, let's make use of equation number 1. That said that dv by dt, the left-hand side here, is minus 500. So let's sub that in. This looks remarkably like the result we were asked to show. All we need to do is to divide both sides by minus 1. So there we have it. We've proved the desired result. Part 2 says, hence, find the age of the car at this instant, giving your answer in years and months to the nearest month. This word hence is really important. It means use something that you've already done to help you to answer this part of the problem. In fact, we're going to use the equation that we've just solved. We're asked to find the age of the car at this instant in years and months to the nearest month. So we're asked to find this value t here. So we need to solve this equation for capital T. The first step is to divide both sides by this number. That gives us this on the left-hand side, which we can simplify to give us this fraction. Next, to extract this capital T from the power, we need to do the opposite of taking exponentials. That's taking logs. In this case, we're going to take logs of base e. That's taking natural logs. So we're going to have ln of the left-hand side equals ln of the right-hand side. The natural log and the exponential here on the right-hand side as inverse functions will cancel one another out, leaving us with the power here. So we have minus 0.25t on the right-hand side. Just writing that a little bit more neatly as a fraction, if I multiply both sides by negative 4, I end up with this result for capital T. Plugging that into my calculator, this gives me an answer in years. You'll recall that t was measured in years. We need to convert that to years and months. So this is 8 plus this decimal. And to convert this decimal into months, we just need to remember that there are 12 months in a year. so we just multiply it by 12. That leads to this result here. And now I need to round this to the nearest month. So the answer is 8 years and 3 months to the nearest month. The model predicts that the value of the car approaches but does not fall below £8. We're asked to state the value of A. There are a couple of different ways of doing this. Let me show you one way. We can consider what happens as t gets really large, as t approaches infinity. Well, this exponential part here will go towards 0 as t becomes really large. So if we plug in 0, we can see that v is going towards 2,300 as t goes towards infinity. Hence, a is 2,300. We can also solve this problem by considering the graph. Let's first consider the graph just of this highlighted part. That looks like this. It's an exponential graph with a negative growth constant. The growth constant here is found in the power. It's negative 0.25. This tells me that the value is decreasing over time rather than increasing. And as we saw using the algebra, as t becomes really large, the exponential part becomes really small, in fact goes towards 0. So we get this horizontal asymptote here, the t-axis, the horizontal axis. If we now add 2,300, the entire graph gets translated upwards by that amount. So this horizontal asymptote gets shifted upwards to this point. So you can see that this is the value that the car approaches but does not fall below. Hence, once again, a equals 2,300. Once you're confident, this kind of question can be answered almost in an instant. That's why it says the word state in this problem. The final part of this question asks us to state a limitation of this model. You can give any suitable reason, such as other factors affecting the price, such as the condition or the mileage. Or you might say something like, if the car has had an accident, it will be worth less than the model predicts. Or it might be the price may go up in the long term as it becomes rare. Or you might say something like £2,300 is too large a value for a car's scrap price. Most cars scrap for around £400. Any suitable reason that states a limitation of this model would be acceptable. But what you can't do is to suggest some other model. So you couldn't get the mark for suggesting other suitable models, such as saying the value may fall by the same amount each year. Let's consider another exam question. Here, we're told the mass of a substance is decreasing exponentially. Its mass is m grams at a time t years. The following table shows certain values of t and m. We're asked to find the values that are missing from the table. So, because it says that the mass is decreasing exponentially, I know that we've got an exponential model. So m describes the mass, t describes the time, in years in this case, m0 describes the initial value of mass when t equals 0, and k describes the growth constant. Because it says the mass is decreasing exponentially, I know that the value of k, the growth constant, is going to be a negative number. Let's make use of this set of values from the table. When t equals 0, m is 200, so substituting into equation 1, we get this. This simplifies as follows. E to the power of 0 is 1, so therefore m0 is 200. As we said, m0 is the initial value. It's the value of m when t equals 0. So actually we could have written that down straight away without needing to substitute in this formula. Let's substitute this back into equation number 1. This gives us our new equation, equation number 2. Next, let's sub in t equals 5 and m equals 160 into this new equation? Well, that gives us this, which simplifies to this after dividing by 200. To get rid of the exponential, we apply the inverse function, the natural log, log to the base e, to both sides. You can think of the natural log and the exponential on the right hand side cancelling one another out, leaving us with the power 5k. The final step is simply to divide both sides by 5. So I'm taking a fifth of the left hand side. That gives me the value of k. Next, let's substitute that back into equation number 2. So I've just simply replaced k with this. Let's write this in a slightly simpler form. I'm going to leave the 1/5 t on the outside, and I'm bringing in the natural log on the inside. You'll remember from your rules of indices that these powers on the right hand side would multiply together to give us the original equation. Why would I do this? The exponential and the natural log inside the bracket there will cancel one another out, leaving me with 4/5. That gives me this new equation, equation number 3. Finally, let's substitute in t equals 10 from the table to give us the missing value of m. So subbing in t equals 10, we get this. And from my calculator, I get m equals 128. Next, let's substitute in t equals 25 into equation number 3. And once again, with a bit of the help from the calculator, we end up with this value. So we can fill in the missing values from the table. Just a quick note here that we started with this equation, which led to m0, the initial value of the mass, being 200, and k being this number. So we end up with this equation for m. However, we equally could have started with this equation. So instead of k as the growth constant, we could have said that the growth constant is minus k. This would have led to the same initial value for the mass, m0 being 200, but it would have led to a different value of k, the same size of number, just with an extra minus sign. So when we substitute this value of k back in to the original equation, we have an extra minus sign. Minus minus gives us plus, which gives us exactly the same equation as before. So actually it wouldn't have mattered which of these two equations that we started with. We'll end up with the same result ultimately if we're careful enough. How could we recognise exponential growth from a table of values like this? Let's see how the algebra might help us to answer this question. This is the exponential growth equation, and if I substitute in t equals 0 here, I get p equals p0, the initial value of p. If I substitute in t equals 1, well, I get p0 e to the k, and you can see that I've simply multiplied by e to the k. Again, if I substitute in t equals 2, I'll end up with this, which again effectively is multiplying again by the same quantity, e to the k. If you multiply e to the k by e to the k, you get e to the 2k. And this pattern continues. To get the next row in the table, I simply multiply by e to the k each time. So note that as t increases by 1, we're multiplying p by the same amount each time. Specifically, we're multiplying by e to the k. So this is how we recognise exponential growth. So returning to the original table, we notice as we increase t by 1, we're multiplying p by the same quantity each time. In this case, we're multiplying by 3. So in fact, e to the k equals 3. Taking natural logs of both sides, I can solve for k, again the natural log and the exponential as inverse functions cancel one another out, leaving me with k equals the natural log of 3. So this is a really quick way that we can work out the growth constant k, just by looking at the table. I hope this video has helped you with modelling exponential growth and decay. It really helps to remember the form of the exponential growth and decay equation. Remember that P0 describes the initial value of P, the value of P when t equals 0. K is the growth constant, and T is simply time. If you like this video, please give us a thumbs up, leave your comments down below, and subscribe to this channel so you'll be the first to know when we release our next videos.